Capacitors. On Thursday, we are going to introduce the inductor, but today just capacitors. We are going to talk about this in terms of AC and DC circuits. But before we get into that, last time we went through and we introduced our parallel plate capacitor. So that has these two equations here. So again, technically for these, it's only for parallel plate capacitors, even though in reality, we very rarely deal with parallel plate capacitors. But mathematically, it's there. We might see those in the conceptual part of exam 3, but outside of that, probably not that big of a deal. We then talked about capacitors in series and in parallel. So for both of these, the equations are flipped compared to the resistors, but the overall concept for what is the same is still true. So when we are looking at capacitors in parallel, they are going to have the same voltage drop across them. Whereas if we look at the same or capacitors in series, here we focus on the charge on those plates, which charge is related to current. So it's the same type of thing, even though it's not the same exact value, that's the same. Any questions from last time? So today we're going to talk about them in DC and then AC circuits. So let's look at an uncharged parallel plate capacitor. So here we have our battery, has some voltage value, and right now the switch is opened. So because the switch is opened, no current is going to be allowed to flow. And eventually, what I might want to go through and do is figure out what charge do I have on that parallel plate capacitor? So that would be the capacitance times the voltage. And if I wanted to find the voltage, well, that would be the charge over the capacitance. Whatever one we happen to be looking for, we technically can go through and utilize. So what's going to happen is we are going to close the switch, and now charge is going to be allowed to flow. We are going to, with this diagram here, again, I don't know why it's flipping back and forth between electron and conventional current. So this is the electron current. So we are building up the charge here on the right plate, which is labeled B. And we are pulling that charge from plate A. So that's what's building up the positive and the negative values. And because charge has to be conserved, we have positive on one plate, negative on the other. If we were to sum those up, it would sum up to 0. So every negative charge, essentially, I've pulled off of the left plate A here. It is now on the right plate B. So eventually this is going to stop. And there's really two situations in which that our parallel plate capacitor is going to stop charging. One is that I just reached the physical capacity of the charge I can have on that parallel plate capacitor. So I could have a maximum amount of charge, which is going to be dependent on that capacitance value. But in reality, when we're going through and designing our circuits, typically we're introducing a parallel plate capacitor where it's not going to be the charge that maxes out first. It's going to be the voltage. So what's going to happen is eventually we get to a maximum voltage value across of our parallel plate capacitor where it's going to have the same charge or same voltage as our battery. And so because they point in opposite directions, they should sum up to what value? And they're going to do 0, right? Because once, if we're thinking about going around the loop in the clockwise direction, I'd add the voltage from the battery, and then I would subtract that same value due to the parallel plate capacitor, because the positive side of the parallel plate capacitor points this, right? It's on the same side as the battery. So they are going to go through and cancel out. And this is going to be how we're typically representing our maximum charge. We have our maximum charge being equal to the capacitance for our parallel plate capacitor times the source voltage value. So this is going to be what we are assuming for our parallel plate capacitors, such that we're going through and we are going to reach that voltage value before we reach the maximum charge. So this is what charging our parallel plate capacitor looks like for a DC source. All right, we're just going to go until we reach that maximum value with whatever it happens to be. We will see sometimes in our circuits for capacitors that it's going to be attached to two different parts of the loop, or two different loops, and we'll have a switch in there where we're going to be either in a charging or a discharging configuration. That is going to be the case when we have a DC source. We'll talk about AC in a little bit here, but for a DC source, we're going to go through and we're going to see charging and discharging situations. We just kind of want to understand what's going on with both of those. Any questions about charging our parallel plate capacitor? So for discharging, what we are going to assume happens is we are taking out our battery and we are replacing it with an ideal wire. Or if we have a more complicated circuit, what we might have is a battery, our parallel plate capacitor, and there's some switch associated with it where that switch can flip back and forth between the charging and discharging sides. So we would charge it with our configuration with it over here to the left, and then we would switch it over to the right to then go through and discharge it. Depending on what we have for our circuit, we'll determine which one of these methods we're technically going through and using, but the physics is going to look the same. So we remove the voltage source, and then because our charges are attracted to each other, they want to go through and interact. But there's a gap here, right? So there's either physically a gap by having vacuum, or we have that dielectric in the middle. So they physically can't just go across the parallel plate capacitor. So instead, they are going to discharge through the ideal wire. So again, here we have the electron current being drawn. So we're having our negative charges move such that it's now able to interact and basically go back to that positive side until the fact that your capacitor is completely discharged. So at this particular point, you will have no charge, right? Both plates will be neutral for the parallel plate capacitor. So with these circuits that we've been looking at here, we've been keeping it isolated from the resistor. So these are just capacitor circuits. And in reality, you're not going to just have a capacitor circuit. It's not very interesting by itself. So often when we go through and deal with this, we are going to start introducing a resistor into the circuit, which is going to get our circuit labeled as an RC circuit. Resistor, capacitor, circuit. And what this is going to go through and do is it's going to start affecting the rate at which the charging and the discharging is going to occur. So before we start kind of exploring that RC circuit, we do want to start understanding what's happening with the charge. Sorry, before we explain it mathematically, we are going to want to explain conceptually what's going on a little bit by introducing that resistor. So before we do that, any questions so far? All right. So again, we are going to go through now and we are going to look at charging or current and voltage. We're going to focus on it right now during charging. So when we're charging, we are going to have our parallel plate capacitor attached to our voltage source. So in this case, we're still dealing with a DC source, so we're going to look at a battery. As soon as this switch closes, we are going to have a maximum value for the current that is flowing to our parallel plate capacitor. So that's what's going on here, where we have a maximum current value. Over here on the right side, we have a second loop where we have the discharging current that we could have for our capacitor. So, all right, we're going to go through and we're going to start charging this capacitor. And as time goes on, do we think the current increases, decreases, or stays the same? Why?
Opposing to the capacitor.
Yeah, why is it going to decrease?
I'm just assuming the positive to the positive kind of slows it down a bit, just kind of like it does the resistor.
Yeah, so the pot right now I have a voltage building up as my current keeps flowing into here. I'm going to start getting a voltage build up here. So the right, I can't, right, if I go through and use Kirchhoff's loop law, these are going to start canceling out, which means the current over time is going to decrease. So as the voltage on the capacitor goes up, the current in the circuit goes down because they start canceling each other out. Eventually, what's going to happen is, again, our source is going to be, the voltage across the capacitor is the same as our source, and then no current would flow through that left loop. Eventually, it is going to stop charging. Again, when we get to Vs across that parallel plate capacitor, we've reached our maximum value. And then we're going to go through and be able to start discharging through our loop. So as we discharge, and let's say we're going through and we're dealing with that right portion over there, do we think current starts at a maximum or a minimum? As we start to discharge.
It starts at a max.
Like,
Just gonna have more energy stored up initially on discharging.
yeah, I have more energy stored up. I have more charges there. I'm going to start at a maximum, and over time, it's going to go to zero. So I'm seeing the same types of behavior for charging and discharging. Or I'm going to start at some maximum current value, and it's eventually going to go to zero. But what's happening with the voltage is the opposite. While I'm charging, I'm going from 0 volts to the value for the source. Whereas when I'm discharging, we're starting at the value of the source and it's going down to 0. And so we need to start going through and figuring out how to explain that behavior. And we'll get to equations here in a second, but just as a reminder, this is possibly not the largest value you could have. Right, this is just for this particular circuit. Because of the way it's set up, we do have a maximum voltage value. So we want to go through, again, there's a couple other little things we want to talk about. And then we can get to our equations. So for this circuit here, on the bottom, we are still keeping that voltage source attached. And so this is going to be kind of a weird situation for the charging and discharging parts where they're constantly going to be fighting each other. So often when we're going to be talking about discharging in this class, we are fully going to be removing that source, whatever it happens to be. And right, we close the switch. Now we can have current flowing on one or both sides, depending on exactly what's going on with the circuits themselves. So over time, again, right, when I'm charging, maximum current goes down to 0. When I'm discharging, maximum current also goes down to 0 as the voltage drops across that resistor. Technically, when I'm using this parallel plate capacitor as my source, it is still technically a voltage source. So this means that if I needed to, I could describe the current with Ohm's law. I would still be able to go through and use V equals IR, but now what's going to happen is over time, that voltage value is going to decrease, and so too is the current value. And this is going to give rise to different behaviors, which means that using Ohm's law is kind of convenient, but also it's not going to be great for explaining how to go through and look at the behaviors over periods of time. Using Ohm's law is only going to get us instantaneous values for the voltage or the current passing through this resistor here. So this means, again, it works, but it's not going to be the best method to go through and calculate values. So there are some ideal things that we are going to be considering before we get to our equations. First is that we are going to be assuming that across the dielectric in between our parallel plate capacitors, we cannot have charging or discharging. We are going to be assuming that this is the most ideal dielectric in there, and no current flows through the parallel plate or the right between those two plates. If we are looking, because we're going to be looking at AC here in a little bit, for a constant voltage source. So our DL batteries or whatever it is, our capacitor is going to appear as an open because of this idealization that we're using. So because we talked about it a little bit last time, right? It's a dielectric, no current flows through that part. We are treating it like an open or a break. If we are utilizing Ohm's law, and this is the part that's a little bit weird, if we're looking at an instantaneous value, we are going to treat the capacitor as a short. So how they are going to behave is going to be dependent on what you would go through and be using it for. But it turns out once we have our equations, using this behavior doesn't really matter because we can just plug in values. We're not quite there at this time. We need one more thing to get into that. So before we introduce our first of multiple time constants, are there any questions so far?
I assume
Yep.
constant and instantaneous voltage, instantaneous is relating to AC. That would,
You can do instantaneous for both. Uh, more often it's utilized for AC. So this is our first time constant equation. And I say first, we will see, that's all right, it's gonna end up being in week 13. We're gonna see multiple time constants pop up as we go through and deal with our other circuits. So here we are doing an RC circuit, a resistor capacitor circuit. And if we look at our equation here for time constant, it's going to be the resistance times the capacitance value. So with the time constant, it is a constant for that particular circuit. And it is going to be dependent technically, if we wanted to go through and be really specific, it's the equivalent resistance and the equivalent capacitance values. So if we have one resistor, one capacitor, we can use those values directly. If we're going through and dealing with multiple resistors, multiple capacitors, technically we should simplify it first into a single resistor, single capacitor, then we can go through and get the time constant. For our time constant, the best practice is going to be making sure that our resistance is in ohms and our capacitance is in farads. If we go through and multiply our ohms times our farads, we are going to get that our time constant pops out in its SI units of seconds. The time constant is something associated with time, should have an SI unit of seconds. You can see milli, micro, nanoseconds as well. Just all going to depend on that circuit. So you might be asking yourself, right? You can multiply two values together. I've seen you guys do it so far in this semester, so I'm not terribly worried about you guys being able to multiply. So we want to think about why this time constant. What about it is special? And the reason it's going to be special is it's going to help us figure out what's considered close enough to being fully charged or fully discharged. And what it's also going to allow us to do is figure out, or not figure out, but help us start comparing. So today we're doing RC. Next week on Tuesday, we're going to do the RL, the resistor inductor circuit. And by using the time constant, the equations that we're going to have for current and voltage are going to look exactly the same. That's only if we're using the time constant variable, not if we're going through and looking at right, R and C versus R divided by L. So any questions before we start seeing our equations? So let's talk about our graphs first. So here we have on our top graph, on our x-axis, we have time, where the time is being measured out in time constants. So here we have 0, 1 through 5 tau for our time constants. And on our y-axis, we have our voltage value. And down here on the bottom, we have our current, or sorry, this is our discharging versus charging one. So here we're charging our parallel plate capacitor. Here we are discharging it. So again, here we have our voltage as a function of time, where we are representing that time with time constants. So if we're looking at this, right, If we're adding up the 1 tau values, we have 63 plus 73. What should those add up to? 100. So it's the same ratio of charging versus discharging as we're going through and looking at it. What do we notice as we get further and further along in time?
Curve starts to flatten.
Yeah, we start to flatten out, and it turns out we are going to be referencing long periods of time. And we're going to put this in quotes for long time here. Because as we go through and do these calculations, we're going to see that a long period of time for the circuit is not at all a long period of time with how we perceive it. But anytime you see a long period of time, this is going to be when time is greater than or equal to 5 times the time constant, whatever it happens to be. So if we're going through and looking at charging at 5 tau, this is when we're 99% fully charged. That's good enough for us. If we want to look at discharging, right, we're at 1% of that final voltage value. That's close enough to 0. Doesn't really matter. If you really wanted to be fully charged versus fully discharged, there are values you can technically go through and utilize, but typically cutoff wise, we just do 5 tau. It's a lot easier to go through and utilize those. So what type of curve does this look like? Yep. So we are going to have some exponentials show up. So for our exponentials here we have our instantaneous velocity, and here we have our instantaneous current. So these are the general equations. So this can be used for charging or for discharging. It doesn't technically matter which one we're dealing with. And instantaneous voltage and instantaneous current here. So if we're looking at the values, let's focus on that voltage equation first. So here we have VM, that final voltage across that particular parallel plate capacitor. And that is gonna, right, if we have a single parallel plate capacitor in our circuit, that would be VS. Right? Eventually it should charge up to the voltage value for our source. And that would be, all right, I would take that, and then I would need to add it. What should, for the charging case, what should my initial voltage value be?
For charging,
For charging.
sure.
Yeah, right? We're gonna assume we're not randomly jumping in halfway here. So I'd have a 0 here, that term's gonna go away. I then have the source, right, it should get to the source voltage value, e to the minus t divided by tau. So it's that t part that's gonna tell us how close or how far we are into finding or getting to that final voltage value. We can do the same type of thing for current, but for current, it's not, the initial current is not 0. It's going to be the maximum for whatever it happens to be. So more often than not for charging and discharging, especially for parallel plate capacitors, we typically focus on the voltage values because we understand what's going on with the voltage better. If we wanted to do the current, we would need to go through and utilize Ohm's law to help us go through and figure it out. So use Ohm's law to find that initial current And that final current value should be 0 for both terms. So, yeah, there's our charging stuff. If we wanted to charge it, it looks like this. And for the sake of current, if we needed that one, we'd have our initial current, which we would be going through using Ohm's law, so it would be resistance value times our with the source voltage, go through and get that, and then I'd have e to the negative t divided by tau. Tau here is our time constant either way. If we're discharging, what should our final voltage value be? So our final voltage value would be 0, which means I would plug in 0 here and 0 here. And so that's going to get me my other equation. It looks like this. So again, this is for voltage. So here we have the instantaneous voltage when we're discharging is equal to the initial value times e to the minus t divided by tau. What do we notice is a little bit different between the two equations for, let's just talk about it in terms of voltage. What's different about the two equations? So it depends, right? We're going for that maximum voltage value for both of them. Right, so in the case of charging, VF is our maximum. In the case of discharging, our maximum occurs at the beginning. What else? That the only difference?
Negative t divided by tau from 1.
Yeah, so we want to make sure that our values are coming out as positive. And so that's where it's kind of going through and we need that term. So with these equations here, technically they can be derived. Sorry, before we get into that, just for the current equation, in case you are curious, it's going to be IF 1 minus e to the minus t divided by tau. So they're flipped from each other. So with these equations, when we're going through and looking at them, right now it just feels like they've come out of nowhere. Right? We're just saying, hey, these are the results based off of these graphs. They are technically derived from going through and utilizing Kirchhoff's loop law. In particular, if you go through and look at textbooks, a lot of the times it'll derive it for the charging case. So if we had, I think I deleted the slide here really quick. Let me just add a blank one in. So let's say we have a circuit and it has a battery, it has a resistor, and it has a parallel plate capacitor. Right, this is just a circuit that it's an RC circuit, and the way it's drawn is going to indicate that we're charging. If I want to go through and do Kirchhoff's loop law, would I add or subtract? Let's say I'm starting below my battery here, and I'm going to go around in the direction of my conventional current. What would I do with the battery voltage value? Add or subtract it?
Add.
Let's just call that Vs. What about for the resistor?
Subtract.
Okay, so that would be whatever the current is times the resistance, and then what about the parallel plate capacitor? Yeah, we would subtract the value, but it's not gonna be IC. Because we don't care about the voltage in terms of current, we care about it in terms of charge, but have minus, sorry, CQ equals 0. So this is our change in voltage across the resistor, and this is our change in voltage across the capacitor. So we could rearrange this such that we have VS. Typically, it's rearranged such that we put the current on one side and leave the charge on the other. We'll talk about why this is the case here in a second. Minus C times Q equals IR. Oh, also, sorry guys, I messed that up. It's not QC, it's Q divided by C. If we think back all the way to the beginning of the semester, we said that current was equal to the amount of charge over time. So we could go through and we could put that relationship in, but technically we want to look at smaller and smaller and smaller times. So as time approaches 0, what do these deltas become?
Smaller.
What mathematical thing are we technically doing as we get closer and closer to 0 for delta t? Taking a limit, so that means that we can transform this into dq over dt. Times the resistance value. Now we can go through and we can rearrange this in a couple of different ways, but this gives us what is referred to as a first order differential equation. It is called a first order because with my derivative that I have in here, it is a single derivative, right? I don't have a right? I'm not doing it squared or anything like that. I have one thing here. So first order differential equation. If we solve this, which is not necessary for this class, we come through, it'll come out. Technically with the signs and how we've done it, we will pop out with this equation here for voltage. So this equation is the solution for the equation we had at the last one. If you had it discharging, you would go through, it sets up a little bit different, but you would go through and you would get this equation here. Because again, we don't have that battery, so the equation looks a little bit different, but it'll pop out as this. We generalize it, this top equation instead pops out. These are the mathematical solutions to the first order differential equation, which again, you are not expected to do for this class. I'll let you know where it's coming from. Any questions about our equations for charging and discharging parallel plate capacitors? We already talked about that part, but again, long time, tau is greater than or equal to 5. Or sorry, t is greater than or equal to 5 tau. All right, so we're gonna go through and we are gonna do 39 here. We're just gonna kind of work, right, determine the time constant. So what do we need to do before we go through and get those values, right? Again, we're looking for tau is equal to RC. What do we need to do first?
Find all the resistors.
Okay. I need to combine all of those resistors. So for the sake of doing this, right, C is going to be a short for us doing our calculation. So what's in what with what? R3 and R4 are in parallel. What about with R2? Yes. What about with R1? No, we have to do those 3 in parallel. And then it's going to be in what with R1?
Series.
So it's going to be R1 plus 1 over R2 plus 1 over R3 plus 1 over R4 inversed. So if we go through and do this, we'll have 1 plus 1 over 2.2 plus 1 over 1, sorry, 1 plus 1 over 1.5 inverse. And that gives us 1.471 kiloohms. What do we want to do next?
Regular ohms versus ohms or doesn't it?
Well, let's think about it. What's the unit for capacitance? What?
No. Or charge.
But it's in farads, but what's it given in? Given in microfarads. Coulomb or kilo is 10 to the what? Yeah, so 10 to the positive 3. What about micro? What is the mu symbol?
10 to the negative 6.
10 to the negative 6. They don't match.
So would that come out in millifarads if you were to just leave it alone?
It would come, so if I leave it alone, it will come out in milliseconds. So if you are uncomfortable mixing and matching your units, best practice will be to convert both of these into their SI units. So if we're being honest, giving the answer like this in microfarads is absolutely silly. I don't like this. Right, we could have just done 2.2 nanofarads. It's the same value. But for the sake of argument, let's say that we're going through and we are gonna convert it just so we can see it done that way. Sound okay? So we have 1471.4 ohms. In here, I'd have 2.2 times 10 to the negative 9 farads. So now that I have those, I can just plug it in. And taking that and plugging it in, I got 3.237 times 10 to the negative 6 seconds. So for the sake of rounding, 3.24 times 10 to the negative 6 seconds. If you had left it in kiloohms and microfarads, your answer would have popped out as 3.24 times 10 to the negative 3 milliseconds. Or we can feel fancy, 3.24 microseconds. All of these are the equivalent time constant values. How we go through and then use this time constant in either of our equations is all going to depend on what t is given in. If we're doing these equations at any form of them here, when I'm dealing with the e value, it needs to be unitless when we go through and get our value. So if t was in milliseconds, leave tau in milliseconds. If t would be in microseconds, we can leave it in tau in microseconds. They just need to match. Doesn't matter what, they just have to match. Any questions about number 39 here? Any questions about capacitors in DC circuits? Right, so we're gonna move on into AC circuits. So for AC circuits, we are going to talk about this a little bit more mathematically to go through and get to our equations. But at the end of the day, it is going to look fairly similar for how we're going to go through and interact with it. So for an AC circuit, right, we can have, right, our voltage or our current source is going to be changing values. So unlike a DC circuit, with a capacitor in an AC circuit, it is constantly charging and discharging. So because, let's say we have a voltage source and it's flipping directions, that is going to cause the capacitor to discharge. And then when we flip it, it'll go back to charging it. So it's going to constantly flip back and forth between charging and discharging. So this means that the relationship between the current and the charge on those parallel plate capacitors is going to be a lot more important. So for the current, when we're talking about it in terms of the AC circuit, we are going to represent it as dq over dt. So we don't want to use I at all. We want to go through and use it in conjunction with what we have. So something that's interesting when we're talking about, again, for our parallel plate capacitor, charge is equal to the capacitance times the voltage. And if the capacitor itself is just a standard capacitor, the capacitance value is fixed. So I can pull that out, and now we have an equation that the current is going to be equal to the capacitance times the voltage that is being taken as the derivative with respect to time. So for this equation here, this is the instantaneous capacitor circuit or current. So this is telling us from the capacitor, how can we go through and calculate the current? And this makes going through and dealing with our parallel plate capacitor a little bit more complicated to go through and figure out. Because now the current from it might be counteracting some of the current from the source. And because the source is constantly changing, we're probably not getting all the way to that saturation point. Right? Because we're constantly going to be charging and discharging. So how we go through and trying to look for the solution is technically a little bit different. So we're going to go through and we're going to talk about graphic or kind of mathematically what we expect our circuit to go through. And that's going to help us figure out the equation that we need to use. So before we do that, any questions so far? Right, so let's consider this circuit here. So we have an AC source and a parallel plate capacitor. And again, we can represent it with a wire here if we wanted to. So what should so let's say we just put this together and we close the switch. What should the capacitor charge start as? And if it's 0, that means that the voltage across this parallel plate capacitor should be what? So if Q equals 0, and Q is equal to CV, if Q is 0, what should V be equal to? Yep. So we're going to assume that our capacitor is starting as neutral or uncharged. And based off of this here, right, we don't know if it's going to start off as positive or negative. But let's say hypothetically, we build up, right, we're going to start building up charge on one of these plates. And it's going to reach either the positive or the negative maximum value. And then the source flips. After it flips, what's going to happen to the voltage across that parallel plate capacitor? Right? If it's flipping, we're going to start discharging our parallel plate capacitor, so that voltage is going to start decreasing. And it's going to decrease to 0, and then it's going to go to the opposite maximum voltage value. And so what's going to keep happening is we're going to keep going through and doing this. We're going to be at, so 0, let's say positive amplitude, 0, negative amplitude, 0, positive amplitude, 0, negative amplitude, 0, and we keep doing that. Sine or cosine? We're starting at 0. We get a very nice looking sine function to go through and explain what's happening. So this here is our voltage. This is, here we're assuming it's in this case, a positive sign, which is some function of time, typically just represented with omega t, but it all kind of depends. If I think about from the last slide, we had this equation, the current from the parallel plate capacitor is equal to C dV over dt. The current is going to be equal to some constant, let's just represent it as K. It's not really specific as to what it is because we don't have exact equations right now. What is the derivative of sine? In this case, sine t with respect to t. Again, whatever happens to be inside of their matches. Sine and cosine. They're the same function. I mean, if we do a phase constant, we can make them equal. But if I put the phase constant in one, the phase constant's also in the other. So what's gonna happen is the current and the voltage are out of phase with each other. And this is where we start needing to we can use the phasor to help us understand how out of phase they are with each other. So before we do that, any questions so far? Yes, it's just some constant, whatever it happens to be based off of our equations.
So cosine represents the current.
Assuming we are starting our time with it completely discharged. Any other questions so far? Oops. So yeah, this is gonna give us kind of our first useful use of the phasor. So here we have the representation. So up here we have our voltage across the parallel plate capacitor, and here we have the current coming from that capacitor. And so they are 90 degrees out of phase. So we could go through and draw those phasors. So here, this is at a specific time. This isn't at a specific time because we don't have maximum voltage at the situation for maximum current. So what this phasor diagram here is doing is it's saying that we get maximum voltage and maximum current at different times, which agrees with what we're seeing here in our diagrams. And with those, they are 90 degrees apart from each other. I can then, if I needed to, draw any other time on here, and I would have some component of voltage and some component of current. And depending on numerical values for my particular circuit, that's going to go through and affect how long that would need to be drawn and what I would need to go through and include. But, you know, it's a way to represent it. So we want to talk a little bit about this AC source. Because in theory, we can go through and we could get the math out of this. But it turns out if we go through and we solve a differential equation to look at the voltage and to go through and look at the current, it is a very specific set of solutions, which then does not build up into more complicated circuits. Our end goal for this class is to look at the RLC circuit, the resistor, inductor, capacitor circuit. And so for that, it turns out there are some math that we can go through and utilize, especially when we have an AC source, that's going to make it such that when we do our AC resistor capacitor circuit, and then we do our AC inductor resistor inductor circuit, and then when we do our AC resistor inductor capacitor circuit, it all starts to look the same. So we're going to build that up instead of trying to just brute force some math to get us some explicit equations. So before we do that, again, are there any questions so far on capacitors and AC circuits? So we are going to introduce our first term of reactance. So what reactance is going to be? It is the opposition to a sinusoidal current. So again, with our AC sources, we are focusing on them being sinusoidal based. So sine or cosine doesn't really matter. As long as it smoothly transitions from positive to negative amplitudes, it doesn't really matter. And what it's going to do is it's going to take our non-resistor components, so in this case, the capacitor, and give us kind of a resistance value to them. So basically, how hard is it for this particular circuit component, or how much does it resist the changing values from the AC source? Now, for resistors, we used resistances as R. So naturally, the next best letter we can use for the reactance is going to be X. So we are going to see two different types, or technically we'll see three different reactances, but only two of them have equations. So here we have X sub C. X is going to be the variable that we use for reactance. And for the parallel plate capacitor, our equation is going to be 1 over 2 pi F, where F is going to be the frequency of our source. And then we have the capacitance, which is the capacitance of the capacitor. So this is going to give rise to some pretty weird stuff. What were the units for resistance? Yep. This has the SI unit of the ohm. So this is a resistance value, and it is indeed measured in ohms. Which means that typically when we're going through and we're plugging in our values, we are going to want to make sure that our frequency and capacitance values are in their SI units, such that it pops out in ohms. So we're here because this is essentially an elaborate way to get resistance values. We can go through and we can now use Ohm's law with it, where instead of R, we got to use XC. And instead of going through, and if we think about all of the things that needed to match for resistors in series and parallel, turns out we can use those for the reactance values as well. So we can now go through and revisit. So we can talk about reactance of a circuit for our RC here, sorry, for just the capacitors. Right, we can go through and we can calculate the capacitive reactance in series and parallel, and we can use them with Ohm's law. So we're going to see those equations on the next slide. But are there any questions on reactance in general or capacitive reactance in specifics? Series looks exactly the same as we saw with resistors, but now it's X sub C 1, 2, 3 instead of just R 1, 2, 3. Something you might see, and I'm gonna be honest, I'm just too lazy to type it out that way. You might see X C or X sub C sub 1. This is another really common notation that you will see utilized. I'm gonna be honest, I'm just a little bit too lazy to subscript my subscripts. So I'm just gonna use C 1, 2, 3, same idea. Just you want to resubscript your subscript. So matches exactly with what we have with resistors. Right? Resistors in series, we just added those values together. Here, when I have the reactance for capacitors, I'm just going to add those together when they're in series. What did I do when I had my resistors in parallel?
Inverse it, and then take the inverse of that summation.
Same thing. Now it's a bunch of X's with a subscript C, and then we have our numbers. What's Ohm's law when we talk about it in terms of resistance? That is one of the many ways. That is the least used way probably for Ohm's law. V equals IR is how we've typically been using it, but its definition is I is equal to V over R, or in the case of reactance, I is equal to Vs divided by XC. So here, technically, that should be the equivalent or the total value that is going into it here. But this is gonna be just a tiny bit more complicated than just replacing it with X, because again, this is for an AC source and an AC source only. There is no reactance for a DC source. Reactance is explicitly for AC. So when we talked about our AC sources, there were a bunch of different ways we could go through and talk about it. We need to make sure that our current and voltage are represented in the same manner, which means I can have peak, peak to peak, RMS, or half wave average to go through and explain either the current or that voltage value. So if I have peak to peak voltage, I will have a peak to peak current. I have the reactance for my capacitor. So any questions before we look at our second example? So we're going to do 49 here. So we're going to be going through and calculating the value of C1. So I want you to look at this here and thinking about what's going on with our capacitors. What might we be able to go through and help us figure out what's happening? You guys want to discuss this the easy way or the hard way? Okay. So we're going to do it the hard way. We do need to establish a couple things that we'll need for the easy way as well. So this here is an RMS value. So what can we state about this 4 milliamp value? What is it probably if we're given an original RMS value? Yeah, it's gonna be an RMS value. For, in particular, this part over here. Other pieces of information that both methods would need. What can we state about C3 and C2? Which means that V2 better be equal to V3. So if we want to do this the hard way, what we're going to need to go through and do is I need to calculate the X value for all three of these, figure out the total current, and then I can find what's going on with C1. That is one way to go through and do it, and it's possible. It's just going to take a couple extra steps. If we want to do it the easy way, what we would go through and do is I can find the voltage across V3. How would I do that?
Cross B3,
Or sorry, C3.
C3.
Yeah, how would I find the value for V3?
You got current and resistance, it's just Ohm's law.
Yep, so V2, right, equals V3, which would be equal to my current, my 4 milliamps, times my resistance value of 700. Or sorry, my reactance value, 750 ohms, which is equal to 3 volts for the RMS. What do I do now? If I want to do it the easy way.
Well, you now know the volts going for C1.
Huh?
Because it's gonna go to 0 once it gets messed up.
But I don't know what that is. What, we can sum up to 0.
Yeah.
Right, delta V RMS. If I go around the circuit, let's say we are starting here. What would I do with the 5? Add or subtract? Minus whatever the value is for 1, minus the value for 3, or yeah, C3, which we just solved for is 3, equals 0. So what is 3 minus, or 5 minus 3? This is the easy way. It is definite. I know we haven't done a lot with capacitors, but treating them the exact same way with their resistors is a little weird. Especially because we spent so much time with resistors and what they did. Suddenly now treating a totally different circuit component the same way. That is okay, if and only if 2 things. 1, AC source, and 2, we are dealing with the reactance values. So by using the X values, that's going to be how we can go through and solve. So this is the easy way. Any questions about that before we talk about the harder way? Okay. So if we want to do it the harder way, we are going to have to go through and try to figure out using reactance what's going on. So we can find X2. Right, that would be 1 over 2 pi FC. If I want to use this, what do I not currently have for X2?
Frequency.
So how do I find the frequency? You might ask, well, to find the frequency, I'm going to need to use X3, 2 pi C3. That's going to get me, right? This is rearranging the reactance equation incorrectly. Hold on, I wrote that down wrong. Don't write that down. Right, because I forgot it's in the bottom. So it's 1 over 2 pi X1 C1, or sorry, 3. That's a 3. That's a 3. So that's gonna give us our frequency, which we can then shove into X2 to get the X2 value. I have no way to solve for X2 directly from C1. I don't have a capacitance value. So instead, what I get to go through and do is try to back calculate with the branch or with the current divider equation, what that's gonna look like. I'm gonna be honest, it's not very fun. In theory, you can do it though. I'm just not gonna recommend it. So as we go through and build up more with our resistor something else circuits, we do need to try to, when we're dealing with reactance, so when we have AC stuff, go back to what we know about resistors and apply it that way. So any questions about capacitors in circuits? All right, I'll see you guys next time and we'll